Hello and welcome to NHP's live webinar on safety input devices and applications. My name is Daniel Nathanson. I'm a commercial engineer for NHP Electrical Engineering, specializing in automation and integration products and solutions, and also a TUV Rhineland accredited functional safety engineer. This is just one in a series of webinars created to showcase NHP's smart devices, powered by smart distribution and embedding smart safety into operational processes, providing our customers with better visibility into processes, data, and analytics. In this session, we will specifically be looking at emergency stop devices, their application, special functions, why and how they should be used with respect to the machine safety standards. This session also continues on a series of live and on-demand webinars on other machine safety topics. If you hadn't had a chance to view some of these, I would highly recommend you head over to the NHP YouTube channel to see more webinars in the series. Some of the key topics we'll cover in this session include the relevant standards for general design and selection of e-stop, the stop categories, emergency stop devices, and their installation requirements. At the highest level, the emergency stop function is called for in AS/NZS 3000 under section 2.3, which describes the requirements for the control of the electrical installation. The general requirements for this section state that the electrical installations shall be provided with devices to prevent or remove hazards associated with the electrical installation, and for maintenance of electrically activated equipment. This involves ensuring that the electrical installation includes switching devices or other means of disconnection for the purposes of isolation, mechanical maintenance, other function control, and, of course, emergency functions, the last of which we are most concerned given today's topic. For the emergency function, we're pointed to clause 2.3.5 for emergency switching, including emergency stopping, which provides us with more granular detail for what devices for emergency switching function should detail. Note the wording of this clause. Means shall be provided where it may be necessary to control the supply to remove an unexpected danger. This means do a risk assessment. Identify the hazards involved with your installation and evaluate the risk. Determine whether an emergency switching device is required, what type of device, what function it performs, etc. For example, if there is risk of electric shock, then the emergency device needs to provide isolation of the supply, so the device will also need to meet the requirements of an isolator. In almost all cases, emergency switching is required for machinery, but it absolutely must be included as part of a risk assessment. I won't be going through every single detail in this clause, rather I'll do my best to outline the requirements as part of a general overview. The purpose of the emergency function is to avert arising or reduce existing hazards to persons, damage to machinery, or to work. It's a safety measure put in place to reduce risk post factum, or after the fact, meaning it's only initiated during an emergency situation, only after an increase in risk has been identified. This could be identified by a person or automatically by the machine control system, for example, over speed monitoring. When the emergency function is required to be actuated by a person, it needs to be done in a single human action. This does not necessarily mean that the emergency stop operator directly shuts off the machine though. Imagine the size of the button and the force required to break open the main feeder to a machine drawing a few hundred amps. What this means is that the person doing the action to initiate the emergency function does so in one action. Press one button, pull on one rope, push on one lever. What you don't want is someone fumbling around with covers and guards, trying to expose the emergency stop button before they can actuate it, or going through a series of actions in order to safely shut down the machine. Which leads to the next point. The decision to use the emergency device does not require the operator to consider the resultant effects. It should be that if you see something dangerous occurring or about to occur, the last thing going through someone's mind should be whether pressing the e-stop button will result in a more hazardous situation. And lastly, one of the more overlooked aspects of an emergency stop, particularly in the machine safety world, is that it is a complementary safety measure only. It does not perform any safeguarding whatsoever. Its only purpose is to lessen the risk associated with a hazard by stopping the machine, but relies on the responsiveness of the person operating it. Remember, you're pressing the e-stop because the dangerous situation has already occurred. By itself, it does nothing to actually safeguard the machine, so other safeguarding measures may be necessary other than the emergency stop function. There are actually quite a few standards to refer to regarding the emergency stop function and devices. AS/NZS 3000, we just saw, mainly deals with the absolute fundamental requirements for the emergency switching function, of which emergency stop is a sub-function. And as AS/NZS 3000 is generally speaking an installation standard, it lends itself more to the installation and identification of emergency switching devices. Whilst it does touch on the design requirements for emergency stop, it is still at a very high level and very much depends on the type of electrical installation you're applying it to. Enter the AS/NZS 4024 series, which is all about safety of machinery. In this series, there are two parts which go into good detail on the emergency stop function with respect to machinery, as is our main topic of concern. Part 1204 is the direct text adoption of the international version, IEC 60204 Part 1, which is an all-encompassing standard on the electrical safety of machinery and does cover off on installation requirements. There is indeed a bit of overlap between it and AS/NZS 3000, but generally speaking, the application of Part 1204 covers everything electrical downstream of the main isolator to the machine. It does provide the necessities for emergency stop function and also includes much of the fundamental requirements like basic function, location, identification. Part 1604 is also a direct text adoption of an international standard, ISO 13850, and is specifically about the requirements and design principles for the emergency stop itself on the machinery. Both 1604 and 1204 go hand in laying out our requirements for the emergency stop function and devices. What I aim to do in this webinar is to combine the requirements of each of these three standards, AS/NZS 3000 included, into an overarching framework of how the emergency stop function is realized for machinery and which satisfies the requirements of all three of these standards. General requirements for the emergency stop function are as follows. The e-stop function shall be available and operational at all times. So no matter what state or mode the machine is, be it in normal operation, configuration, maintenance, etc., if the emergency stop function is required by the risk assessment, it has to be available. This extends to where the operator might be located during these modes. If they are inside a robot cell performing configuration or programming, they need to have an emergency stop operator available to them inside as well as out. Speaking of all modes of operation, the e-stop function, when actuated, must override all other functions and operations of the machine and in all modes. It shall also not impair any facilities designed to release trapped persons. Going back to our robot programmer example in the robot cell. If the emergency stop function is actuated, they cannot be trapped inside the cell. This ties into the selection of the locking devices and mechanisms. If the e-stop is pressed and the machine loses all power, and the guard is held locked by a power to release solenoid, well, there's no power to energize the solenoid to release the lock. So other mechanical means must be made available to trapped persons to release the guards. With guard interlock switches, this can be realized as a mechanical manual release button. It shall also not be possible for any start command to affect operations which have been stopped by the e-stop function until manually reset. So the first thing to note there is that when the e-stop is actuated, it remains latched in that state until it is manually reset. And whilst it is latched, it disables any other operational functions. The main goal of this requirement is so that you cannot start the machine until the e-stop is released. This forces you to acknowledge that the e-stop has been actuated in the first place, and there must have been a good reason why it was done. It may also prompt the operator to check that all hazards have been cleared before resetting. There is some exception to this rule, however. Even after the e-stop is actuated, some auxiliary safety functions may still be required. For example, we may require the careful jogging of a machine to release a trapped person or allow the engaging or release of brakes, etc. Any additional functions allowed whilst the emergency stop is activated should be severely limited to only those required to reduce any further risk. They need to be carefully considered and addressed as part of a detailed risk assessment. This brings us to the requirements that the e-stop shall not impair the effectiveness of protective devices or of devices with other safety functions. There may be other safeguards in place which must remain in place even after the e-stop is pressed. Take, for example, a machine with a high rundown time that is protected by a locked guard. When the emergency stop is actuated, the machine may take an appreciable amount of time to slow down to a safe speed to ground access. You do not want to be able to have to access through the guard whilst the machine is still running, or running down for that matter. Other safeguards which monitor the speed of the machine and controlling guard accesses need to be operational while the emergency stop is active. And of course, I already mentioned this, but I'll say it time and time again, An emergency stop is not a substitute for other safeguarding measures. It is a complementary measure only and does not perform any actual guarding. Your risk assessment should guide you as to what level of safeguarding is required. Determining what the machine needs to do during an emergency stop needs to be well thought out or well ahead of time, preferably during the design of the machine. When actuated, the emergency stop must cease all hazardous movements and operations without creating any additional hazards in the process and without requiring any further intervention by any persons. For example, this could mean selecting which functions are shut down, remembering that some other safeguards may be necessary even after the emergency stop function is actuated. Determining the stopping profile of the machine. Can it coast to stop, or does it need to be controlled with a specific deceleration rate? Is braking required? Do other actions need to be taken in a specific sequence to safely shut down the machine? This all needs to be considered and implemented when designing the emergency stop function. Using the e-stop does not require the operator to consider the resultant effects. A person's reaction to an emergency should be to hit that e-stop operator immediately. The safety control system should take care of the rest. The emergency stop needs to stop the machine, and there are several methods in which this can be done, depending on the risk assessment. In AS 4024, Part 1204, these are described as stop categories and are part of what goes on in the background after the e-stop is actuated. For emergency stop operations, we are only concerned with two stop categories, 0 and 1. A category 0 stop is the immediate removal of power to the machine, or mechanical disconnection between the load and the motor. If actuated in the middle of operation, the motor will decelerate in an uncontrolled manner. We can use it in an emergency stop application in accordance with this standard. However, this may not be the best course of action, particularly if the machine has a high inertia load and takes a long time to slow down, or could cause another hazard if stopped in the middle of a process. In many applications, motors cannot simply be isolated and left to coast to a stop, as this could cause an intolerable risk. An uncontrolled rundown of this type often takes considerably longer than controlled braking or deceleration. What we can do instead is to initiate a controlled stop by ramping down the motor, or initiate a braking function before completely removing power. Only when the motor is at standstill or has reached a safe speed is power removed. This is called stop category 1. This type of controlled stop is often used with variable speed drive or variable frequency drives, which permit ramping down or dynamic braking. Once the ramp down has run its course, the drive is shut down safely. The reaction times are reduced compared with allowing the motor to coast down. As a result, in many cases, the safety distances to the hazard can also be reduced. This provides a number of benefits such as improved ergonomics for the plant operator, space savings due to the reduced distance between guards and the hazard, and of course cost savings. Let's have a look at an example of both stop category 0 and 1 circuits using safety monitoring relays. In this example, we have a simple on-off safety monitoring relay, a GSR-SI. It has an emergency stop operator as the input and a PowerFlex 525 variable speed drive as the output. When the e-stop operator is pressed, its contacts close and the safety monitoring relay is ready to accept a reset command. When reset, it closes its output contacts, which apply power to the safe torque off, enabling signals going into the drive, and also to the stop-start operators, so the drive can be used normally. When the e-stop is actuated, the contacts open, and the safety monitoring relay in turn opens the contacts to the drive. The safe torque off signals go low, and all torque power being generated by the drive disappears. The motor no longer has any torque power and just coasts to a stop. For a category 1 stop, we require something a little bit different. In this case, we need to issue a stop command to the drive to initiate a controlled ramp to stop before removing power. In the example shown here, we're using a guard interlock switch to guard the hazardous area created by the motor and an emergency stop operator to safely shut down the machine in the event of an emergency. There are several safety functions going on in this example, including interlocking, guard locking, and prevention of unexpected startup. But for the sake of brevity, we will only look at the emergency stop function offered by the emergency stop operator. So let's take inventory. As before, we have a GSR-SI safety monitoring relay, which performs a simple on-off functionality. And controlling it is our e-stop operator. A signal from the GSR-SI goes into another safety monitoring relay, the GSR-GLT, which is a specialized guard locking safety monitoring relay with built-in time delay. This is used to automatically unlock the guard after a set time delay, ensuring that the machine has reached a safe state before allowing access. Coming out of the GLT are three signals. One is to the stop-start signals to the drive, and a pair controlling the safe talk-off inputs. From the last example, we saw that if you remove power to the safe talk-off signals, the drive removes torque power to the motor and it initiates an uncontrolled stop. This isn't what we want. Rather, we want to send a stop command to the drive first, allowing it to stop in a controlled manner, and then only after a time delay when the motor has slowed down, disconnect the STO signals and remove power. This is a Category 1 stop. So our e-stop is reset, signal goes out to the GLT, the guard is closed and locked, and we give a door lock and reset command. The drive has all input signals and can be operated normally via stop and start operators. In an emergency, the e-stop is pressed. The signal between the two safety monitoring relays is removed, and the GLT begins its actions. Firstly, it removes power from Y32, which provides the stop-start signals to the drive. In doing this, the drive is given a stop command, the same as it would if a normal stop button were pressed. The drive begins to ramp the motor down. Meanwhile, the GLT has started a timer which is preset to the expected ramp to stop time of the drive. When the timer has expired, the GLT removes power to the safe torque-off signals and all torque power is removed. At this point, the motor has already ceased motion and the Category 1 stop is complete. Another condition of the emergency stop function is how it is reset after being actuated, and we saw that there were reset commands being given in the examples earlier. Once actuated, the actions which perform the emergency stop must be held in place until they are manually reset. If, for example, the action is to remove power from a control circuit, then it must remain in the off position and hold this state continuously until someone comes and resets it. A lot of this ties into the type of emergency stop operator that is used, and we will take a look at the various devices shortly. They need to be latching so that when they're actuated, they stay there. When you do go to reset the e-stop, it shall only be possible at the location where the e-stop command was initiated, or as near as possible depending on the type of device. This is done to ensure that at least some level of inspection of what might have caused the e-stop to be pressed in the first place. It's an emergency device, so something dangerous may have occurred. You want to have checked that the dangerous condition has been cleared before the machine can be started again. It also ensures that by resetting the e-stop device, you're ensuring that, that it is functional and available for the next time it may be used. An important one, the resetting of the e-stop shall not restart the machinery, but only permit restarting. There is a difference in the wording between reset and restart. The reset is to clear the conditions back to a default state. In the case of the e-stop, this is to revert it back to its unactuated state and permit power to the control circuit, if this is the normal case. Restarting, however, is the actual startup of the machine, putting it back into a moving and operational state. When the e-stop is reset, the machine should not start up automatically. It requires manual intervention to start the machine after an emergency stop command has been given. Depending on the risk assessment of the machine, the safety control system may require another manual reset button on top of the reset of the actuator itself. And lastly, it shall not be possible to restart the machine until a manual reset of all actuated e-stop devices has been performed. This means that if there are multiple e-stop devices around the machine, it's possible that more than one e-stop device was actuated. Your reset of the e-stop needs to occur locally at each of the e-stops which have been actuated. This ensures, again, that the dangerous conditions are likely to have been checked and cleared at the locations where the e-stops are located, and that they are available for the next possible demand. The devices which are used for the e-stop function can be quite varied, and they are allowed to be, as there isn't always a one-size-fits-all device which covers all applications. Regardless of what you select or design into your machine, it needs to allow easy actuation by the operator and anyone else who may need to actuate it. Typical actuator types for e-stops include, but not necessarily limited to, mushroom-type push buttons. This is a traditional emergency stop button, and these are to be palm operated. There has been an update to the AS4024 series, which includes the latest version of the emergency stop standard ISO 13850, where this was clearly defined. And I'll explain more about this shortly, because there is a good reason why this was done. Wires, ropes, and bars, these are most ideal where the availability of an e-stop actuator needs to be across a wide area and where multiple push buttons are just simply not practical. And other devices like handles and foot pedals can be used. Again, depending on the type of work, being able to access an e-stop easily and as quickly as possible may not be practical with push buttons. So hitting a bar like in mobile wood chippers or a foot pedal may be better. Regardless of what device you choose, the requirements for their operation are the same. The e-stop device shall use direct opening action with mechanical latching. What this means is that firstly, the contacts are normally closed and the physical force of pushing the operator must force the contacts open. It cannot rely on non-resilient or non-rigid parts to open the contacts like springs. This ensures that if the contacts are stuck closed due to tack welding or oxidation or similar, the force of you pushing that button forces them open regardless. Mechanical latching. This means that once the contacts are open, they're latched into that position and stay open until they are manually reset back to the closed position. This is part of our reset requirements we saw earlier. The e-stop device must also be designed and tested in accordance with IEC or ASNZS 60947 Part 5.5. This is the standard for electrical emergency stop devices and covers off on all the design requirements and testing procedures the device needs to comply with. So things like the minimum force required to actuate, voltage and current ratings of the contacts, durability, robustness, environment, shock and vibration and impact, etc. We mentioned before with regards to the reset that it can only be possible as a result of a manual action at the location where the e-stop was actuated. You'll notice on the example e-stop devices below that there are facilities for this manual reset. On the pull wire switch to the far left, there is a reset rod which must be pushed in to reset the contacts. Second from the left is a blue lever which is twisted to reset. Second from the right is a blue reset button. And on the far right is an emergency stop button which requires the twisting of the operator counterclockwise to reset, and then the operator pops back out. You may also find that with e-stop buttons that they may also be a pull to reset, where the operator is pulled back out from the actuated position. So the e-stop condition has to be sustained, but in the event that we get a failure of the mechanism which holds the contacts open in the actuated position, the emergency stop command must still have top priority. This is one of the reasons why we have a separate manual reset button in the safety control system, which ensures that if the emergency stop command is given, that the machine cannot be restarted until everything has been acknowledged and reset. Now, is this e-stop station acceptable? There is an old school of thought regarding colors and sense of hazards and safety, and there have been many studies on the matter. Red and yellow are often associated with hazard or urgency, whereas green is seen as safe. So the question is, what color should we make our device? Is it for a feeling of safety, so make it green, or is it for a sense of emergency, so let's make it red? We actually see this disparity with emergency exit signs. The red color is used in the Americas and other parts of the world, whereas green as a symbol, green with symbols, is used in Australia and New Zealand, Europe, etc. Red gives us a sense of emergency, so we run to the red emergency exit sign. Or green gives us the sense of safety, so we run to the safe color of the green emergency exit sign. You can see the jury is still out on this one as far as human response to color is concerned. So then our emergency stop button, is it green for safe or red for emergency? No. In Australia and in most parts of the world, the actuator of the e-stop device shall be coloured red, and it has been standardised this way so that it is easily identifiable. Red is for emergency situations. Now, there is no requirement to have a background behind the operator, but if there is, and as far as it is practical, the background shall be yellow. Again, red and yellow being the colours of hazard or emergency. In the latest version of AS 4024 Part 1604, there is a new recommendation that neither the actuator or the background be labelled with text or symbols. This extends to things like labels on the operator itself or labels behind it which might say emergency stop or similar. Instead, it's suggested that the IC symbol shown here is used. I use the words suggestion and recommendation as the text in the standard is provided as a should and not a shall. So the issue of labeling is not a strict requirement, but it is a fairly strong recommendation to move towards the practice of using symbols instead of text. The preference is to have no labeling and rely on the colors and symbols to indicate the emergency stop function. What about locations? Where should the e-stop devices be located around the machine? Short answer, anywhere a person will be located whilst operating the machine. This is the default, but you can perform a risk assessment to determine if perhaps it's not needed at that specific location. The risk assessment will also determine if additional e-stop devices are required at other locations, for example, at entrance and exit locations, locations where intervention to the machinery is needed, like where you would use a hold to run or enabling switch, or at all places where human-machine interaction is expected by design, like loading and unloading areas. Regardless of where it's located, the e-stop device must be positioned so that it is directly accessible and capable of non-hazardous actuation by the operator and others who could need to actuate them. The new standard AS4024 Part 1604 goes on to state that the e-stop actuator intended to be operated by hand should be mounted between 0.6 and 1.7 meters above the access level or the floor or the platform level. This basically means the e-stop should be within arm's reach whilst standing. E-stops using foot pedals should be mounted in a fixed position directly at access level, so on the floor. One of the main gripes of requiring an emergency stop is that at some point or another, someone is going to hit the e-stop in a non-emergency. This could easily be done purely by accident. If the e-stop is located somewhere where someone may bump into it and shut down the whole machine, this kind of nuisance tripping always spells bad news for production. What is typically done in this situation is to put a guard around the e-stop operator to simply stop someone from accidentally hitting it. The problem with a lot of these guard solutions is that they usually work too well. If you do need to use the e-stop in an emergency, the guard often prevents hitting the actuator as intended, adding unnecessary steps or manipulation to expose the actuator. In an emergency, timing is critical, and these additional guards only serve to add time to the responsiveness of the e-stop operation. What should be done, though, is to put in additional precautions to prevent accidental actuation in the first place. Relocate the e-stop away from foreseeable heavily trafficked areas. Review the type, size, and shape of the e-stop device, or mount it within a recessed surface of the surrounding control panel. The use of a guard or shroud should be the last resort where other measures are not practical. If there is the need to guard the e-stop from unintended actuation, then any measures you put in place shall not create a risk of obstruction of the actuation or impair access, nor should it impair the visibility of the e-stop or its actuator. For hand-operated e-stops, any guard you put in place shall not impede or hinder actuation with the palm of the hand. This is specifically the reason why mushroom-type push buttons in the latest standard have been worded so that they are to be operated with the palm to prevent excessive guarding around the e-stop operator. So, with this in mind, of these three e-stop guard options, which one is the odd one out? The one on the left has a guard covering the whole actuator. Does this allow operation with the palm of the hand? Well, yes, it does, but you have to lift the guard first, so actuation of the e-stop requires more than one human action. Remember, the emergency stop function shall be able to be initiated by a single human action. This is no good. What about the one on the far right? This one is guarded against unintended actuation and isn't really covered, so you could actuate it with a single human action. But what about palm operation? Well, definitely not. I would need to use a finger or a thumb to get in there to hit the e-stop button. This guard is impairing access by impeding the intended method of actuation, which for a button like this is with the palm of the hand. This is no good either. So what about the middle one? It is guarded with a shroud, but this does not cover the actuator, so it's still readily exposed. It is still readily it is still easily identifiable. What about actuation with the palm? Well, because the shroud is adequately spaced from the actuator, I can certainly get my palm in there in one action to hit the actuator. So, is it acceptable? Yes. This is how an e-stop can be guarded with a shroud without impairing access, visibility, or proper operation. What about wires or ropes as actuators? These are used as an alternative for large areas where emergency stop operation is required throughout the area, as the personnel around the machine could be at any location. This is typical of conveyors where applying multiple equally spaced e-stop buttons every meter or so is not really practical. When applying ropes or wires as the emergency stop actuator, there needs to be careful consideration regarding their positioning and ease of use. So consider the amount of deflection of the rope necessary to generate the stop command and the maximum deflection possible. No more than a few tens of centimeters of movement and the rope should be required when pulling on it. Make sure there is sufficient clearance between the rope and the nearest object in the vicinity. There should be enough space behind the rope to get your hand around it to grip the rope. And also, when pulling on the rope, there should be nothing in the way to prevent you from pulling it with the required deflection. Make sure the rope is clearly visible. This is generally done by the color of the rope, red. But if additional visibility is needed, then use marker flags, which can be red and yellow. Consider the amount of force required to pull on the rope in order to get the amount of deflection needed to actuate the e-stop. And this should be the force in any direction, such as along the axis or perpendicular to the axis. When it comes to performing the reset of the emergency pull wire switch, it's important to note that it may have been pulled anywhere along the entire length of the rope. If it spans the whole conveyor or production line, this could be many tens of meters long, even over 100 meters. The idea of having to locally reset the emergency stop device is to ensure that there are no hazards still present when the emergency stop was actuated. For emergency pull wire switches, you need to ensure that the entire length of the rope actuator is visible from the reset location. But this is not always practical, as the rope can span long distances or bend around corners, or there may be other visual obstructions. So if it is not possible to adequately inspect the machine from the reset location, then you need to have instructions for use in place so that before reset is permitted, that the entire length must be inspected. Consider pulling the rope along the axis, so either directly towards or away from the switch. You must ensure that pulling on the rope in either direction results in the actuation of the e-stop. This is actually an important requirement under the application standard for safety of conveyors, AS 4024 Part 3610. Actually, a feature of this ability to operate the switch by pulling in any direction lends itself to another requirement, where breakage or slackening of the rope must result in the generation of an e-stop command. This is because emergency pull wire switches are constantly under tension. Pulling on the rope away from the switch increases the tension and then trips the switch, whereas pulling towards the switch decreases the tension, which has the same effect as the rope slackening or breaking. The requirement of being able to pull a rope in any direction and generate an emergency stop command has implications on how the rope is affixed to the machine or other structures. Let's look at an example where the rope is firmly anchored on the far right end of the switch, which unfortunately does happen in some installations. Pulling on the rope away from the conveyor or perpendicular to the axis of the rope will trip the switch as it's applying extra tension to the rope. This is fine. Also, pulling on the rope along the axis away from the switch will also trip it. But what happens when you try and pull along the axis towards the switch? You're pulling against a rigid object. The rope will not slacken this way, and the e-stop will not trip. This is not an acceptable mounting arrangement. In this case, what is required is a tension spring on the other end of the rope, which gives the operator something to pull against and create slack in the rope. Alternatively, a second emergency pull wire switch can be fixed on the other end of the rope, as its own internal tension spring can provide the same effect for the other. And so concludes today's webinar on emergency stop devices. By now you should have some more intimate knowledge on the many requirements for emergency stop in machine safety applications, understand which of the relevant standards are used for design and selection, and details on the various emergency stop devices and installation requirements. For some more in-depth examples on these safety devices and applications, head over to Rockwell Automation's webpage on safety function documents. Here you'll find a wide variety of application technique documents, which include information on setup and wiring, bill of materials, configuration, verification and validation plans, and calculation of performance level. For more information on the selection or even just on machine safety in general, there's a wealth of information available in the NHP Machine Safety Selection Guide. I also highly recommend reading through the Rockwell Automation Machinery Safebook 5, which is a bit more advanced but provides fantastic guidance around the designing and navigation of machine safety control systems. Thank you for joining us for this webinar. I hope you found it beneficial. To find more webinars in this series, please go to nhp.com.au or our dedicated NHP YouTube channel. And if you have any further questions about machine safety products and solutions, please contact your local NHP sales representative. With smarter and faster decision-making and seamless connectivity spurring new collaboration, NHP is enabling the connected enterprise. Thank you again, and I'll see you next time.